So hello, everyone. Thanks for coming to this talk called What is Pure Functional Programming and How It Can Improve Our Application Testing, which is a pretty long title for a talk. I hope you enjoy that. You may have heard this thing somewhere or somewhere on the internet, or may have read that. You may say, okay, pure functional programming is pretty big these days, and it helps testing, but is this really true? Because I read an article that says it's not true. So I don't really know. No, I'm joking. No, I know. Spoiler, it is. But no, I didn't want. But it came to my mind that I may have used another title for this talk, which is How Pure Functional Programming Helps Us Avoiding Bugs in Our Code, which is the real topic of this. But we'll see that later. So about me. My name is Luca Molteni. That underneath is my Twitter account. So if you want to send me something. I work for a Canadian company called BitGold. We do digital payments with gold, which is a pretty big thing these days. We do it using functional programming, so it's pretty cool, although we use Scala. Sorry. So yeah, no, that's OK. So why I decided to do this talk? Because pure functional programming and testing are two of my favorite topics. I always speak about that. Everyone that knows me knows that I speak every day about pure functional programming and testing. But why? Why I do that? It's an important question to do because I think that pure functional programming is fun. I think it's a very relaxing style of programming. And it helps you think about your code in a more modern way. So I think it's very relaxing. And lately, I think that the concept of functional programming are considered real and usable in every other programming language that is not functional, actually functional. Imagine, as an example, Java 8. Java 8 decided to take a lot of features, one lambda expression, from functional programming, but that means that it is really important these days. Is there anyone here that uses functional programming at work every day? Only one. That's few. But you do know functional programming, really? Yeah, because everyone these days is talking about functional programming. Raise your hand if you know functional programming. Yeah, lovely. How many of you do? How many of you do know about pure functional programming? 1, 2. Oh, that's not bad. I thought it were less. So it's not only that pure functional programming is fun, it's also that testing is fun. This is more like a controversial topic because I may be the only one that thinks that testing is fun. Everyone I talk with, they say, OK, no, testing is not fun. Testing is boring. I should avoid tests at all. I don't really care about testing. I heard such things every day. Is there anyone here in the room that totally thinks that test is not worth it? No, not even one. I mean, maybe it's a strong expression. Who doesn't like to do tests, to write tests? One. Her laughing. No, I can see you really well because I've got a light in my face, but I saw some hands. So it's, I don't know why, but I think that testing is fun. It's relaxing, as pure functional programming, but especially it's fun because I like the idea of breaking my code. I like the idea of creating some strange situation where my code breaks. And these situations are not always obvious. There are some strange situations you don't know really why, and the code breaks. And I love to find such situation. So today, I'm going to try and change their mind to those who think that writing tests is not worth it, although there is no such thing. Because what we should really strive for is code quality. I personally think that the code quality these days is still too low. We ship software with too many bugs. I mean, that's a fact. I mean, I just opened my smartphone 5 minutes ago, and I opened an app, and it crashed without telling anything. That's a bug, guys. We're shipping really bugged code. And we know, that's the point, we know that there are different methods to remove bugs from our code, but we decided not to use it. And I can't understand why. And obviously, as you may think, pure functional programming and testing are two of these tools. And we'll see in this talk when to use it, or how to use it, and if we should use it. So let's say that we should find the best way to remove bugs in our code in the best situation. You okay? What do you think? So that's what we are talking this evening. We're talking about a little introduction on what is pure functional programming. Lucky us, you already know functional programming. I mean, those who don't, just ask me. I'll tell you later. Then we talk about testing, a little bit about testing, and then type systems, which is a pretty big topic these days. And then I see some conclusion. What do you think? Are there any questions now? No, because I haven't started yet. Well, never mind. Okay, what is functional programming? You already know that. Obviously, we don't like to agree on definitions. So basically, there is no scientific definition of what functional programming is. But there are these two topics which we almost agree about, which is the first one is that the functions are first class. It means that functions are values which can be used in exactly the same way as other sort of value. That means such as an integer, a string. A function is just a value. And it's very easy to define functions, otherwise it wouldn't be called functional programming, as you imagine. And then it's easy to pass function as parameters. And it's also easy to return function as return values from other functions, which is kind of brain twisting if you think about it, but once you get used to it, it's very powerful. And the other thing, which I'm going to see today, that the functional programming languages are focused around evaluating expressions rather than executing instructions. So we don't have really much time to see what an expression is. So you have to trust me, because we're talking about testing today and not expression. But let's say that the difference between expression and function, and instruction, it's more like when we are defining expression, we are trying to say to our programming language, to our runtime, what we want to do instead of how we want to do, okay? Just take this really small definition, which is not kind of good, but that serves our purpose for today. So if we know what an expression is, we can now understand what is a pure functional programming. It's a specific style, a subset of a normal functional programming, where every expression is considered pure, okay? So pure functional programming is a simple functional programming language where every expression, which are the base of functional programming, are considered pure. And what does pure means? Pure means that an expression that is pure has this property called referential transparency. I repeat it again, referential transparency, okay? Which, as I said before, we don't agree on the definition of referential transparency. So if you search on the internet, you find plenty of definition of referential transparency, and some of that are true, some of that are not true, are false, and some of that are the programmers are saying that we shouldn't really use this expression of referential transparency. But let's try to read a definition that I've chosen randomly. No, I'm joking. An expression is said to be referentially transparent if it can be replaced with its value without changing the behavior of a program. That is a pretty important definition. To understand the first definition, we have to understand the substitution model, which is not the topic of today, I'm sorry. So I really hope that you go in and check out the substitution model of functional programming languages. But let's read the other part of the definition, which is the most interesting thing. In other words, yielding a program that has the same effects and output on the same input. Okay? So we could say that a program written in a pure functional programming language is a program that gives me the same input, the same output, given the same input. Okay? Do you agree on that? I hope so. Let's see the first example of an expression in Haskell. This is a very simple expression, almost too simple. Someone said me to use a much complicated expression, which I put in the presentation, so don't worry. So this is a Haskell code snippet. Haskell is a very esoteric language. You don't really want, no, we were talking about Haskell. And you see the definition of this expression is split in two parts. The first part is the type signature. And then this means that it is a function that takes an integer and then takes another integer and returns an integer and just sums it. And it's pretty easy to understand, isn't it? I mean, it just takes two numbers and sums them. Every time I call it, every time I call sum of 2 and 3, I'm always getting 5. Okay? And every time I'm calling sum of 3 and 3, I'm always getting 6. So if I now try again and call it sum of 2 and 3, I will get 5. Let's see another example. This one is written in Java. Okay, the programmer who wrote this function decides to make a joke on me. And instead, he called this function sum, which has the same, do you all know Java, really? Because we are a Java conference. No, I'm joking. The type signature is the same. The name of a function is the same. It's called sum. It takes two parameters, a and b, and returns another parameter, which is, I think, it's the sum. But what it does, this function, instead of summing, of just simply summing these two integers, it sums the integer and somehow it puts the integer in a database. And somehow it just gets the integer in the database. As you can see, the first line is just reading a table with a default of b. So what's the tricky part about this function? The tricky part is that the first time I call this function with 2 and 3, I'm getting 5. Which is okay. We ship our code to production and say, okay, sum of 2 or 3, we're getting 5. Then we reload our page, we're getting 7. How's that possible? Okay, because, I mean, we developers are really fun. We like to make jokes on each other. We like to write such a bad code as this. But what can we tell about this snippet of code? This is for sure, it's not an expression, but anyway, we won't care about it, but especially this is not pure. We're not getting the same output given the same input. That's an important thing. But please note that you can write the exact same function as before, as we've seen in Haskell in Java, and it has the same exact semantics. This takes two numbers and sums them, okay? This always, I'm getting the same result given the same input. This is in fact a pure function written in a pure programming language. That's important. Why is it important? It's important because you cannot do going tomorrow on Friday to your boss and say something like that. Okay, I saw a talk about Luca speaking about pure functional programming, and he said that we should program in Haskell every day. You cannot do that. But we can. But what we can do is to learn from this concept and try to apply this concept in our programming languages, which are not pure. Okay. So, as a matter of fact, this isn't a pure function too. This is almost the same as before. I mean, it just sums the two integer and returns it, but there's a side effect. Okay, so this function is not free of side effects. You see, what is this? Okay, this just logs the last executed file, the last executed sum in a file. Okay, this is not a pure function. This is pretty important. So what are the pure functional programming languages? Haskell is the first one, although someone says it's not really pure, so I don't want to start a language war now, so we won't talk about it. So the other one is Clean. Have you ever heard about Clean? Is there anyone that heard about Clean? No one. Yeah, one, maybe, I don't know. I can see it. So Clean is very, much more esoteric than Haskell. It's totally different, but we won't talk about Clean today. Have you ever heard of Excel, the programming language? So Excel is a spreadsheet written by a big company called Microsoft, and it's just basically a table when you put, no, I'm joking. Everyone knows Excel, but everyone, I want that you think about that Excel is actually a pure functional programming language in a way that every time you do a computation, that computation is always a calculation and is always pure. You cannot make a side effect inside an Excel spreadsheet. Although probably someone tried to do that, but I'm not pretty sure. I know that someone writes really complex programming in Excel, but I think that we should all use Excel to write our programs because it's pure, it's easy to test, something like that. And then I put Scala and Java. So Java, you can imagine that because we saw the example of a pure function before. And I put Scala because Scala is the language I use every day, and is a functional programming language that takes a lot of concepts from Haskell, especially in the libraries. So now we have this Scala ecosystem split in two, basically. Those who want to do pure functional programming and those who want to program in a style that is more similar to Java. But you see, you can, it's not important today. So let's try to test pure code, shall we? When a function only responds to its visible inputs, we can easily state properties of its behavior that should always be true. What does it mean, this thing? This means that if we are getting the same output given the same input, a test is far much easier than if it's not. So let's see some examples together. I took this example from this book, so we can say that I've stolen it. I'm just getting inspired. This is a very important book. It's called Functional Programming in Scala, and it's written by Paul Cusano and Runar Biasson, published by Manning. I'm suggesting you to buy this book. This book is really important. This is not a book about Scala at all. I mean, it uses Scala as a programming language for this example, but this is actually a book on pure functional programming languages, which is kind of cool, because I didn't know that. So let's try to take the example. These are the examples from the first chapter. So I've got this program. It's an untestable cafe. It's more like a Starbucks application. And we got a function. This is Scala code. You see def buy coffee. I needed a pointer, but never mind. I used the clock. So there is this buy coffee function that takes a credit card and creates a coffee and returns a coffee. And also, it charges my credit card with the amount due to buy this coffee. So this coffee costs €1 because we used to be in Italy, but we're not now anymore. So probably now it's 4 francs. How do you say francs? Never mind. So what we're doing now is we're trying to call this class, which is the credit card, which is the implementation of the direct implementation of this class. And this class is really stupid because once in 4 times, sometimes it just crashes. And sometimes it calls a web service. When it calls a web service, we get charged of €1. Okay. This is something I like to call an untestable cafe, because it's really impossible to test this kind of application. If you want to test, we could have written a test like this. A cafe should be able to charge an amount. Okay, I created my untestable cafe. I called the buy coffee method passing a credit card, and then I hope that everything was correct. But what if I got charged of €2 instead of €1? What if I got charged of €10? I don't know that, because I have no way to test that what I wanted to do effectively worked. So what I have to do is just success. If the test goes, I mean, it's green, perfect. Let's move on. What we do in Java, but we do the same in Scala, it was try to abstract the idea of a payment. Okay, so instead of calling directly my credit card service, which calls actually a server and does thing, call a web service, what we do is the abstract the thing of a payment, and then we create this trait, which is actually an interface for that. And you say, okay, I've got this method that it should charge an amount if I pass a credit card and an amount. And now I always create this coffee because I still want to drink this coffee. But instead of calling directly the method charge on the credit card, I'm calling a service, which is an interface for a service. This is what we usually do when we want to have some testable thing in the Java world. So we have to use mocks to do that, to inspect the state of my payment processor. Or we could supply a fake payment processor. This is just an idea. So we create a testable cafe, and then we create a mock for my payment, which is basically a class that doesn't do anything. And then I create a credit card, and then I try to buy coffee with my mock, and then I verify that I've got charged for, yes, I've got charged for €1. Which is kind of cool, because at least we're trying to test the behavior of our program. And this should work as we intended. But could we do better than this? We could try that and use the power of pure functional programming and write this kind of thing. So this is kind of a pure function, which is the main difference from this function, from the one you have seen before, is that it returns both a coffee, which is the coffee I'd like to drink, and a charge. A charge is a concept of my card being charged, or I should have been charged in some way. We don't know how. But now the method is far much simpler and does less thing. And now it is also very simple to test this kind of test. Because once you have as return values all the arguments I'd like to test, I'd like to write an assertion on it, I could just test that the amount of I've got charge is just €1. You can see how much simpler this test is. Okay, but you can tell me, okay, Luca, but this method is totally different from the one before. I won't say that. Yeah, no, it's very different, because what we are doing here, we're defined that in this line where we're calling p charge, we are getting a side effect. Sometimes something has to change. My web server should be called, my bank account should be charged over this €1. What we're saying here is just, okay, we're not dealing with charging here. We're only dealing with our business internal logic. I know that if I buy a coffee, I got charged for €1. And if I buy 2 coffee, I will be charged of €2. And there is no side effects here. It just means that after having called this function, I have to call another function that would actually do the side effect. I'm not telling you that you have to write such programs that doesn't do any side effect at all, because otherwise you have to interact with the real world. What I'm telling you is that you have to separate the side effect part from the pure part, because the pure part of our program is the part that we want to test. You get that? What do you think? Are you sleeping, guys? Some of you are, some of you not. So it's pretty much evident now that pure functional programming helps unit testing. Unit testing is the simplest kind of test we have, and now it's getting really even simpler, because we avoided using mocks, which is fine. And what we're getting, we're also getting a very fast system, because we are sure that we don't have to deal with external system at all. So this test will be very fast to run, which is kind of important. But do we have something better than unit testing? Because we see in a while that unit testing is actually simple, is actually very readable, but it's actually not really powerful. So of course we have something more powerful than unit testing. But to get to that, I would like to introduce you the concept of entropy in the inputs. So the entropy means how much my input changes. And I would like to show you a snippet of a code that I found in our production code. Just don't tell anyone. At least, no, I obfuscated that. Hopefully. No, I think so. No, okay, I'm sorry. So this is a test I found in my application, and what it does, first of all, this is an integration test. It's not a unit test. This is actually calling a database. Okay, what I'm doing is I'm creating a random string as a username. Then I am calling a database insert method that obviously insert my user in the database, passing the random string generated. And then I try to query the database to get the user back. And then I check, I make 2 assertions on this test. The first assertion that I got 1 row inserted, and the second assertion is that the row I get from the database is equals to the row I generated in the beginning of the test. Do you see any problem with this test? It's a random test. Is that a problem? It is a problem. I don't know why. No, actually, the thing that is random is actually a good thing, because we're trying to generate it with a random value instead of writing a value. I think that it might be, in some sense, even much more convenient than writing a fixed string. What's the problem here? The problem is that we are generating a random string, and this is making our test really fragile. This test is fragile, and because we don't know how much, an example, the string could be, this random string could be, I don't know, 5 characters, 40 characters, and we don't really know in the database how much characters we allow for the username string. But that is a problem of implementation. The problem of a test is that we are generating only one random value each time we run the test. That's the main problem. If we discover an error here and our test suite is red, you run this test suite again, and maybe it's green. This test is not deterministic. And we are programmers, we shouldn't like things that are not deterministic, but we apparently like because we continue to write such tests as this one. So, you see the problem. If you run, take an example, if you run your test suite, I mean something like 500 times a day, you get only 500 different random values, okay? Which is very few, because our computer cannot generate a lot of random values. So what I like to call this kind of test is a pseudo-random test. So it was a test that it was born to, the developer that wrote this test thought that it was doing a smart thing by randomizing the input. But it was actually doing a very bad thing, because we're getting our test fragile and fragile, even more fragile than what it is. And we don't like fragile tests. We like deterministic, consistent tests. What do you think? What it was trying to achieve is something called property-based testing, which is a totally different thing. I mean, not totally different thing. It's always a test. It always deals with random values, but it has a totally different approaches. So what we do now, this is a property-based test taken from our application too. We generated 2 kinds of a string, and then we got, we try to call this method called process string, which is a method that generates a fixed length string. And we are always sure that this string will be of 891 letters. Okay. What is the difference between this test and the test we've seen before? The property-based testing suite, the property-based testing framework, generates a lots of random value each time I run this test. So we could say that this test was kind of a beginning of a property-based test framework, but in a wrong way, because we are only generating a random value each time I run the test. So what we really want, I want a system that can generate really random values in the way we want. And this is something called a generator. You see, a model generator. You see, this is a class made of 2 strings called tag and an element. And we are generating an arbitrary string for a tag and an arbitrary string for an element. And then we are calling our test suite. And this suite, will generate thousands or 10,000s of random inputs. And we say, if it fails, from which input it will phase. What do you think? This is called property-based testing because it uses properties instead of assertions. And properties are a much powerful concept than an assertion. But that doesn't mean that we shouldn't use assertion at all. We have 2 different concepts, and we have to know when to use properties and when to use assertion. But first of all, I would like to ask you, how can pure functional programming have property-based testing? It should be pretty evident so far, but if it's not, I'm telling you, if a function is impure and I'm calling it 1,000 times with different inputs, it may be really a nightmare trying to reset the external state. So it's important that we get the same output given the same input, because in that way, if we generate again, we hopefully can find the same input value, same random input value that make the test crashes, not pass. What do you think? Beware of readability. Property-based test is not the solution to all of our problems. First of all, because writing properties is far much harder than writing assertion. And properties, rather than assertion, still lack some readability. This is an Haskell code, again, and can you understand what's written there? No, probably no, because you don't know the Haskell programming language. But this is a property that, if this typical property in the tutorial of property-based testing, that says that if we take a string and reverse it again, we're getting the same string as before, which is a kind of cool property to have in our code, but it's totally unreadable. I mean, when we're trying to understand what our program does, we don't really care if we reverse the string 2 times, we're getting the same string as before. We want to understand how a function should be called, what are the expected input, what are the expected output. These properties are really important to prevent bugs in our code, but they're not totally readable. The second one, I won't even read it. So if you guys know TDD, test-driven development, I can tell you that there is some crazy guy that tried to do test-driven development using property-based testing. And the results are pretty much interesting. No, it's a crazy thing. You cannot really do, I'm telling you, you cannot really do property-based testing, property-based testing-driven development. It's too complicated to pronounce. It's really complicated because test-driven development works in a way that you think the test before writing your implementation. And normally, properties are pretty much different, harder to understand before having actually written your code. Well, let's move on. Everything is clear now? Do you have any question? No, fine. We move to the other argument, the side effects and mocks. I know no one really likes side effects. No, I don't like side effects at all, as you may imagine. But I don't like mocks at all, too. But no one really likes mocks. I don't know why. Maybe because of this. Okay, this is another snippet of code that I stolen from my previous company. And this is a code which I obfuscated, of course. And this is a code taken from a really famous e-commerce written in Java. As you can see, this is a really nice example of what does testing with mocking means. The function under test, the method under test is this function filter, do filter. We take a request and a response and a filter change, whatever it is, and it doesn't return anything. It just does side effects, and then we're verifying side effects. What's the problem with this kind of style? This is a heavily mock-oriented style. Especially, the first big problem is that this thing, let's see. No, I can't find it. Never mind. So the first thing is that to write such tests, you have to actually know the implementation. So you cannot really try to black box testing. You cannot just pass some input and verify that something has happened. To verify something like that, to write an assertion of that instead, you see this verification, because while using mockings, all the assertions are called verification. To write such a verification, you have to know that in the implementation of a test, there is a method called copy file internal if needed. And I have to pass this some name, I don't know, it's total. If you write this test and then you try to read it again after 1 month, you won't understand a thing. And if this test breaks, you will curse a lot, because you have to see the implementation, see the order of the mocks, and see that something has changed, something like that. So can we do better? Yes, of course we can. But we take another example. That example is lost forever. This e-commerce, that e-commerce is lost. Never use it. I won't tell the name of e-commerce, but never use e-commerce written in Java. I'm joking. So this is a mockable class, as the example we've seen before. What we did, we have this method, do complicated stuff, which is our internal logic. And we take something from the database and we zip it with something from the network with an HTTP call. And then we do some logic. And if the DB stuff is major than 1, do something else. As we've seen before, this is totally testable method, because we can pass mocks and we can do verification. We can do stuffing. We can do whatever we want. But it's actually really inconvenient to do that. So let's try in the first place to try to avoid stubbing. Stubbing is the act of making an external service return always a constant value. How can we do that? If you want to try to use the concept from functional programming, this is Scala, by the way, I haven't told it yet, sorry. what we're going to do, instead of passing interfaces, what are we going to do is just pass functions. These are the functions that interacts with our real world. So there is this, instead of having a trait that interacts with a database called database, we know that we have a function that is called getDBStuff, and then we have another call called HTTPStuff that takes our parameter and returns a future of a DBStuff, an asynchronous call. And then the exact logic is the same. This is more like a syntactical way to change our code, but it works kind of better because now we can use the high order function to stub our services, which is fine. But we can do even better. We're trying to avoid mocking and writing something like this. You see, instead of a trace, there are two functions, getDBStuff and HTTPStuff. The internal logic is the same, but this time, the value we want to inspect it's in the return value. See, this future result. This function returns an OK or a not found. This is now a totally pure function, and it's really easable to test. And we avoided stubbing, and we avoided mocking. And everyone is happy, and everyone won't tell me, Luca, why are you using a mocking framework for that? OK, is that clear? So the idea here is to separate the pure from the impure part, because probably in all your application, you have a part that is pure, which is your actually logic, and then another part that is totally different, that interacts with the word. And that part is full of side effects. It's not pure, and it's really hard to test. And I'm not pretty sure that you should do unit testing on it. If you can isolate these two parts, the pure part from the impure part, you can do unit testing and property-based testing on the pure part. And then maybe some integration test. No, you should really do integration test, by the way, on the impure part. OK? But let's move on. We can do even better. Because now we have this function written in Java, which is a complex interaction. This is the typical function you will see the first job you will get, maybe in a bank or a big corporation. This is a complex interaction method that takes an user and then calls the first service, the HTTP service, passing the first name, last name, the address, the cap code, and the phone number, and then calls the database, passing the first name, last name, address, cap code. It's really boring. Really boring. I almost fell asleep by reading it. But how can we test a method like this with a very few logic? There is no logic. Can you see some ifs in that? No, there are no such logic. This method will always have the same call, the same order, will never change. Okay. How can we test this? This is an example that obviously used mocks to test something like this. So we're creating a stub. This time we're creating by ourselves. We're creating a user. And then we're passing the user. And then we're verifying that the HTTP client got called with the first name, last name, address. And then we verified that the database got called with the first name, address, and the last name and phone number. Can you see a problem with that? Can anyone try? Does anyone want to try? 1, 2, 3. No. The problem is now we're not testing anything. The only thing we are testing is that the order of the argument is the same, which is kind of weak properties. But this test is actually what I like to call, I don't know if it's an exact definition, but it's a mirror test. It's a test that mimics the implementation one by one. As you can see, the test and the implementation is actually the same. We have two codes here, and we have two verifications there. Okay, in the same order. And once you have to add a parameter to the implementation, you have to add a parameter to this. And once you remove a parameter from the implementation, you have to remove a parameter from the test. And it is not good. This is also a fragile test. And it won't give you anything good. This test is not important. This is the kind of a test that you would write only if you have some requirements, such as every 90% of our code should be tested, which is a very stupid thing. The problem is, what should we test? Do we really need to test this code? I don't think so. The problem is that it's really hard to write tests. It's really hard to know when we have to write a test and when we have to write an integration test, when you have to write a property base, a unit test. That's the problem with testing. If you read some books about testing, they will say, someone will say that you have to start from the edge cases, and some will say that you have to start from the simple cases. What I'm suggesting you is, in this case, when you have a few logic, try to avoid testing. Sorry. What I'm saying is the old debate, which I don't think that it personally is a debate, it's a test versus type system. Test and type system are two different things. They do different value. I'm sorry, they do different things. But they sometimes just collide because they verify the same properties. But there are two different systems. And we have to understand when to use our system or the other system. Let's take this example. This is written in JavaScript, a language I love, as you can imagine. And this is actually a true example taken from the Unit.js website, which is a framework for writing tests in JavaScript. Can you see what it's doing here? Can anyone tell me? It's great, isn't it? What we're doing is the assertion. We are verifying the type of the return values. We're actually trying to mimicking a type system in JavaScript because we don't have a type system. This is crazy stuff, guys. You shouldn't really do this. I mean, I don't know why the guys from Unit.js write such a test. What we should do, we should try that our return value, num, is 5. Not that it is a number, because we don't have any guarantees that in JavaScript, every return values from this function is a number. We can get number undefined, not a number. Or we couldn't even write this very same thing in Java. I don't know, probably no one has written such things. What we're trying to do here, we're writing an assertion, and we're trying to see that the class returned from the say hello method is a string, is equal to a class of a string. That is crazy stuff. We're trying to mimic in the compile, the type system, I'm sorry, with a test. So no one really does that. And by the way, this test won't even work in Java, even if it has a strong type system, because it may have a subclass of a class and that may fail. Or it may throw an exception, because remember that exceptions break referential transparency. Okay? So if your programming language allows you to throw an exception, it doesn't mean that that method cannot be pure. Okay? So type system versus test. The problem is to understand when we have to get some rapid feedback, and that rapid feedback should be very easy should let us avoid bugs in our code. So the type system and the test system gives us feedbacks in two different times. Especially the type system gives us feedback at compile time, while test gives us feedbacks at runtime. That doesn't mean one system is faster than the other, because, for example, if you have to run your application and your application runs in an application server, it may take something like 1 minute to run. So the test there will take 1 minute. So we cannot say that really tests are always faster than compilers. A type system, we could say that type systems are faster than the test, but it's not even true, because if you ever try Scala, you see that the Scala compiler is really slow. Sorry, I have to tell you. Plus, there is a problem with this kind of feedback. This is an error I got from the Scala compiler. Can you read that? I'm going to read it for you. Cannot be instantiated to expected type, monad of, I don't know, of Scala Z, of R of type lambda, in 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 type lambda. Okay, so what I wanted to show you here, that it's not always true that the type system gives you better feedback than the test. Okay? This error message is totally unreadable. No one can really read this. But that is not always the case, because this is an example from another programming language called Elm, which is similar to Haskell, which has a very beautiful error message. Yeah, I have to read it, I'm sorry. The third element of this list is an expected type of value. All elements should be the same type of value so that we can iterate over the list without running into unexpected values. That is pure art. I'm sorry, guys, I have to tell you. I wish that every programming language was like this. Okay? Because what is the problem now? The problem is that if you want to use effectively our type system, the type checker should never be smarter than the developer. Because if the type checker is smarter than you, knows that the code that you have written is wrong, he has to tell you. And you have to understand him. But this causes friction. This causes a fight between you and the type system. And everyone will say, OK, type systems are complicated, and something like that. So let's try to conclude a little bit. What I'm telling you is that use unit testing to give examples of your API. OK, that's easy. Use property-based testing when you want to verify properties. And use type system when you have no logic at all. And all you have to verify is that the arguments are passed in the right type and the right way. And also, be careful using type inference. I'm sorry, I don't have time to explain type inference because it's only 5 minutes left. I got only 5 minutes left. But type inference is a system that helps us avoid writing our type in our system. But I'm suggesting you do not use it if you can. Because the problem is that when you're using type inference, you're not using the type system to design your code. You're just letting the hard part to the type system. The problem is that you will get error messages such as the one we've seen before. What do you think? I've got 5 minutes with the question or without the question at all. So let's skip the bonus, which was dependent types. Whoops, whoops, whoops. And let's go to the conclusion. So pure functional programming leads to a more testable code. Shall we agree on that? If you're going to use pure functional programming, now you will have a strong type system and a very powerful one. Then use it, okay? Because modern type system help us finding bugs in a more efficient way while designing our application. And when the logic is limited, rely on a type system. What do you think? Are you sleeping? Is there any question, really? I'm really interested. This is the first time I made this talk. And this is a topic I'm really passionate about, so I'm eager for feedback. Is there anyone there? OK, do I have any opinion on Lisps? I love Lisps. It's not, but Lisps are not pure functional programming languages, as you may know. Although there probably is an implementation of Lisp, which is also a pure functional programming language. There's typed racket, which I think. This is not about. We had a conference last year in Italy. It was called LambdaCon. And some of you made some guys made the exact question to a speaker after having talked about something like 1 hour, 2 hours about monad and applicative functors and really complicated stuff. And I say, OK, but I'm using Lisp. How can I do this? And he says something like, OK, in Lisp, you don't have this. So if you're using Lisp, you're using a very powerful language, really syntax-oriented, but you don't have really these features. You have to understand that. And once you have understood that, you can decide and choose it, whatever you use it or not. Any other question? Come on, don't be shy. Sorry, look like a mess. That's the end. I hope that you enjoyed this presentation. Thank you for your time. I love, as I told you before, I love to add feedback about this presentation. And this is my Twitter account again. This is my email if you want to send me an email about this argument and speak about pure functional programming and testing. And that's it. Do we have some minutes left? How much? How many? Couple. Let's go back, speak about dependent types. So we want to see dependent types today, of course, because dependent types is a really complicated feature from the type system. I've put it in the presentation because I would like to show you where are we going as computer scientists, what we are discovering. This is a concept that comes from computer science, and we haven't used it yet. But it's really powerful, and we almost trying to use that. So let's try this classical example of dependent types. We're trying to summing to lists. So there are 2 different ways to test something like that. The first one is to test the actual argument, the actual return value of a list. So I'm passing you a list of 1, 2, and I'm concatenating to a list of a 3 or a 4. And what I'm verifying, what I'm asserting there, is that the list that I'm getting is 1, 2, 3, 4. It's pretty coherent. The other way is that we're just trying to make an assertion of a number of elements of a list. As you can see, in a very simple example like this, it's not really clear which one is the best. Do you have some stronger opinion on that? Maybe the first one is better, the second one is better? No. Okay, so the problem is we don't have really, there is no a nicer way than the other. Oh, these two tests are both worth it, but the second test is really useless because the first test always implies the second test. But the first test is stronger, so it may breaks. Okay. So what we're doing now is I'm showing you some strange code, which is a programming language called Idris, which was derived from Haskell, but has this feature called dependent types. And as you can see, it's almost as the same as the function as before we see in Haskell, is seen on 3 lines. We don't see that. The only difference is that we're trying here to concatenate 2 different vectors. And the first one is a vector of n elements, where n is a fixed value. And the second element is a vector of m values. And what I'm getting from that is a vector of n plus m elements. That is a really powerful feature. It means that every time we call concatenate on that, we're always getting a vector, a list. A vector is better in this case, because that's fixed element, of the very exact amount of elements. And if you write a wrong implementation, you get something like that from the type system, saying something like, I was expecting a list of n plus m elements, but what I got is a list of, I don't know, n plus n element. It's impossible to write an implementation of concatenate in IDIS, which is wrong. And I dare you to demonstrate the opposite. No, I'm joking. It's probably possible. But it's really easy to avoid bugs because it's really hard to write an incorrect implementation of these 2 things. And this is due to these dependent types, which has types that depends on value. In this case, my vector types depends on the number of elements of a vector. So basically, I don't have a vector anymore. It's something like a vector of 5 elements, a vector of 4 elements. Okay, you got that. So that's it. This is another example. Thank you again, and that's the end.